a double check just to make sure. I'm kind of sad this is the last one in my streak. I am like trying to figure out a way to do something tomorrow.
Oh, really? What's you got a free day tomorrow?
Yeah.
Gosh, well, maybe it's the chai versus coffee, and then to make Zach happy, you can have versus what's the creatine, whatever they put in their shakes, to get to build the muscles. I don't know.
I don't bodybuild. I just run.
Yeah, yeah. I'm just walking, so that's the progression. You go bodybuilding to running to walking to just getting out of bed. So I'm getting closer to that.
Awesome. We'll live and to the audience who's wondering, Wade and I always have a lovely chat behind the scenes. That's what you were hearing. But without getting too much in the way, this is the third session in the series. Welcome back, everyone, and thanks for joining. I see Mateo in the chat. Welcome, Mateo. I see Korean. Korean, it's always great to see you. Welcome back. We'll be learning about token classification with fastai and blur. And Wade is the real host. I'll just be monitoring the chat and asking him questions whenever he asks me to keep an eye out. So, as a reminder, please keep the questions coming. I'm actively looking at them, and Wade will be actively answering them. With that, over to you, Wade.
Awesome. All right. Thanks, Anya. Let me share my screen. All right. Welcome, everybody. Yeah, this is, as Sanyam said, this is part three of, or session three of the part two of the Hugging Face course. And this is kind of the more exciting part because part seven goes through actually end-to-end examples of the main NLP task, which is probably what everybody's really interested in. And so we're going to spend the next few weeks looking at those mostly individually, except when we get to language modeling, we'll combine looking at causal with mass language models. But today we're going to do look at token classification. Next week, we're going to look at question answering. There's going to be a 1 week break, and then we're going to come back and look at language modeling, and then summarization and translation. Those are the main tasks. So again, I won't go through all this a third time, but we have a bunch of resources. There's a registration group if there's folks looking still to join the study group. There's also a study group Discord that's part of the fast.ai Discord, and so the links will be available in the slides. And then, of course, there's a bunch of helpful links for learning fast.ai or looking at some of the fast.ai Hugging Face libraries. And or just studying machine learning and data science in general. So again, as we get into section 7, I'm going to encourage everyone, if they haven't done so already, as we go through each of these tasks, to at least spend the following week going through the official course, because there are things that I'm not covering. In particular, the courses teach you how to use the trainer API to train these models, and also how to use accelerate slash standard PyTorch loops as well. And also they provide more information about things you need to do for configuration and in those occasions where you want to actually take what you trained and push them to the hub and be able to use through like their inference widgets and things like that. So make sure you check that out this week, especially for the token classification. So this week, we're really going to just go through an end-to-end example of training a token classification, in particular, a named entity recognition model with fastai and blur. And these steps are going to be steps that we follow for just about every task. First is getting a data set that we can use for the task. Second, we are going to go through how to fetch our Hugging Face objects. Third, talk about optional pre-processing we can do with the datasets library or with pandas. Then we're going to go through how to create a data block that can either work with pre-processed data or can actually do the tokenization at batch time on the fly. And after that, once we have our data block, we're going to look at how to construct a learner with the appropriate metrics, and then we're going to train. And lastly, we're going to go through looking at how we can export our model for user use and for deployment, and how we can use the model for inference. So we're going to roughly follow the same steps for every single task. But first, something was bothering me, and the question came up last week about why we can't just use fast.ai to train transformers. And what bothered me is my answer. And I was thinking about it, I was like, man, I feel like I went way in depth, but I didn't really answer the question about why we can't use fast.ai. But the better answer is that Blur is fast.ai. And for this to make sense, if you haven't already, I have a link here in the slides. The folks at fast.ai, so Jeremy Howard and Sylvan Guger, they actually wrote a paper called fast.ai, a layered API for deep learning. And one of the things that folks that are kind of just starting with fast.ai and haven't really got into the weeds don't understand is that it's actually a tiered API. So there's a high-level API where you can do things in one line. There's a mid-level API where you code a little bit more. So you're doing a little bit more on the data block side, or maybe creating data loaders from PyTorch data sets. And then there's also a low-level API. And the low-level API is composed of things like transforms and callbacks and a certain way for doing metrics. And to really kind of see what I'm saying when I say that Blur is fast.ai, I really recommend folks to read this paper, regardless of where you're starting with machine learning and deep learning in particular. You'll be able to read it. It's a very readable, very approachable paper. But take a look at that paper and then pull up the Blur GitHub and look at some of the core modules for data and for modeling, and you'll see just how much Blur really is fast.ai. It's really built on top of fast.ai and all these kind of low-level concepts. So really encourage you to do that. And again, this is the paper right here, and you can find this through archive. Like I said, very readable. And yeah, check this stuff out, and you'll see like this low-level API. You go through Blur, and you'll be like, oh yeah, this really is just fast.ai. It's just really built on the low-level versus the mid or high-level stuff. So that's just an FYI. I feel better now with that answer, by the way. So with that, let's go ahead and begin looking at how to do token classification. So with any task, you want to figure out what is a good data set to start with. And when you start actually building your own models for whatever task you're doing, a good way to kind of figure out how to structure your own custom data set is by looking at some of the experimental data sets that we can use that are available online. So fast.ai actually has data sets that you can grab for many of these tasks. Hugging Face has a tremendous number of data sets that you can download for just all kinds of tasks. And so you want to look at something that you can use for token classification. And probably the best data set is the co-NNL 2003 data set. And I like it because not only do you get the inputs, the text, but you also get the labels for 3 types of token classification tasks: named entity recognition, part of speech, and chunking. And so you can actually use that one data set and play around with all 3 of those kind of sub token classification tasks. The big thing to remember here is that the inputs should be a list of words. So instead of getting some raw text or a text pair, in token classification, when we're building a model, we want to work against list of words. And that kind of reminds me that when I talk about words and tokens, I'm going to be real intentional about those words, because one of the confusing things when you start working with transformers is that a lot of times words, tokens, subtokens get kind of mixed up and used to refer to different things. So I'm going to be real intentional, at least today, I hope, when I talk about words versus tokens. So words are going to be the individual things in a list that have a label associated to it. The tokens are going to refer to all the tokens that make up a particular word. And as we've seen before, since we're working mostly with subword tokenizers, we're going to have, especially for rare words, we're going to have multiple tokens that make up a single word. So I'm going to try to be faithful and use those terms correctly. So again, what we're looking for is a data set where the inputs are a list of words and the labels are a list of labels, one for each word. So let's go ahead and look at this in Colab. I'll make this a little bit bigger. And also I should state here that when this is available and you run this, you're going to notice that I actually did something else that you may hate me for, but I think in the long run will be better. And that is I started renaming a lot of the objects and methods in Blur, and I got rid of the HF prefix since it's given that Blur is a fastai Hugging Face integration library. And I've also renamed some of the callbacks and some of the transforms to indicate exactly what they're doing versus just calling them generically before batch transform or after batch transform. And I'm going to go back and be correcting the notebooks from session 1 and session 2, and we'll let you know when those are all correct. But you'll see some of that. Don't hate me too much. I think in the long run, it will be better. So with that disclaimer out of the way, when we get a data set, again, should be really familiar by now. We can use the load data set and pass in the name of the data set that we're looking for. Look at what's in it, and we can see, as I mentioned before, this is a nice data set because even though they call it tokens, and again, they're really words, right? They're going to be split up into tokens, but okay, they're called tokens in the data set. And then we have 3 potential tasks that we can train our token classification model on: the part of speech, the chunking, or named entity recognition. And what's nice is that we can look at data sets, and this is just good advice in general, is to kind of understand what some of these things look at. And the best way to do that is by looking at a few examples to make sure that what you believe these things look like is what they look like. Because when you start building your data block API, you're going to be building it to how these inputs are structured and how the labels are structured. So we can look at a few examples. And one thing that's different in the Hugging Face data sets versus most of the fast.ai data sets and the things you see in the FAST book is that the labels are already encoded. So they represent the indices in the labels list. Whereas in fast.ai, you would actually see like, B per 0, O, O, B log, I log, etc. And Blur can work with either one of those formats. So once we look at the examples, we can see that we can look at the different labels and see what each of these all look like. And then we can actually, since we're going to work with the named entity recognition task, we can go ahead and actually pull the labels that we're going to be working with specifically in this example. And this is an important step because when we get to building our Hugging Face objects, we need to tell it how many labels there are. And we can go ahead and just get the length of this list, and then we're good to go. So that's step 1. Step 2 is to get our Hugging Face objects. And we need to do this whether or not we're using the optional preprocessing. And you can do this however you want. So in Blur, we provide this utility class just called Blur, and we have get HF objects that accepts a variety of options. So you can actually use this, or you can actually build the objects from scratch, just kind of like how you normally would if you copy and pasted the code that Hugging Face gives you when you are looking at a model. So in this example, we'll just go ahead and stick with uh, the get HF objects function. And again, it accepts all kinds of stuff. Like you can pass in quarks to building your config, your tokenizer, your model. You can pass in specific classes that it should use for your config, tokenizer, a model, etc. So just about anything you can do in multiple lines in building these objects, you should be able to do with this particular method. So we're going to go ahead and use the auto model for token classification. And this will allow us to even experiment with different pre-trained checkpoints since we're not using an architecture specific model. And for this example, I'm just going to set the max sequence length to 128. And as I mentioned before, we're going to need to tell Hugging Face, in particular the configuration object, how many labels there are. If you don't do this and you start running your code, you are guaranteed to see one of the most obscure CUDA errors of all time, which is the device assert error. And literally, it's not going to be helpful at all. But it's going to be because you probably didn't specify the number of labels. And in fact, most questions I get are folks that are having issues with Blur. I would say maybe 60, 70% of the time, it comes down to just not setting the labels for any of the classification tasks. So yeah, make sure you do this at the top so you don't forget. And here, I'm just going to pass the information into Blur, our checkpoint, the class that we want to use, and also the some quarks I want to pass to the configuration object as it's built. Also, if you look at the course material, you'll see that there's other things you can do in here if you plan on pushing your model to the hub and you desire to use their inference widgets, which are really kind of cool ways for folks to see what your model does, and also for yourself to see what your model does. So check out the course content for more information there. So there we are. Step 2, get our Hugging Face objects. So once we have that, an optional task that we can do is to pre-process the raw data. And in pre-processing, essentially what we're going to do is go through our text, and we're going to convert those to the input IDs. So remember that when the tokenizer sees your text, it returns something called a batch encoding object. And that batch encoding object has a bunch of, it basically is a dictionary of a bunch of different IDs for different things. So there's your input IDs, which are the token IDs of the tokens that represent your text. It has like an attention mask, and you can ask it to return other dictionaries with other information. But the input IDs is really what we're looking to create here. And in order to, and not only input IDs, but also we need to adjust our labels. Because as we mentioned before, when we pass our text to a tokenizer, a given word, it could take one or many tokens to represent that word. And so we have to figure out, well, in those cases where there's going to be multiple subtokens, how are we going to label those subtokens? And as I mentioned last week, Blur supports 3 strategies, but you can go ahead and extend and create your own subclass of base labeling strategy and create your own. By default, it's going to use the first token strategy, I believe. we'll look at that in a second, which basically says if it's split up for the purposes of calculating the loss and also the predicted token, we're going to look at the first token, regardless of whether there's one or many tokens that represent that word. But you can go ahead and create your own. But we need to use that for pre-processing so that not only are we creating input IDs, but we're also creating a modified list of labels, one for each of the tokens now, just as in the raw, we have one for each of the words. And then also, this isn't in Blur yet, but one of the things that I'm working on, it's there, but not quite working 100%, at least on the modeling side, is I am working on making Blur able to handle long documents for token classification. And you usually see this for question answering, where the context could be really long and the question could be at the end and you don't want to miss it. But I'm going to attempt to actually also apply this to token classification more as an experiment to see if it works. And if it does, it's great, because then folks working with long documents will be able to just pass them at inference time into Blur and be able to have token classification without having to chunk those things up ahead of time. So I plan to have this at the release of version 2, which will come sometime after this study group. So if we go back to our example here, oops. Where did my, hold on for a second. Oops, there we go. I lost my slides. Let's go ahead and look at the pre-processing just to see what that looks like. And we'll actually use the pre-processed data set in today's example. So I'm going to go and actually take just the training data set and convert it to a data frame. This is something else in Blur. I have to add better support for pre-processing data sets. For myself, I'm more comfortable working with data frames, and I normally find that the data set isn't all that big that I'm working on fine-tuning, and so the performance hit isn't something that's going to keep me up at night. So I'm going to just convert it to a data frame for this particular data set. And in Blur, one of the new things we're doing is providing a bunch of preprocessors for all the tasks that know how to preprocess the data correctly for your given task. So we have token classification, and you can look at this class in the documentation or on GitHub, but essentially it's going to go through and it's going to give us input IDs, and it's going to give us a modified list of labels based on whatever labeling strategy we pass, so that we have the correct label per token, given the labels associated per word. And at the end of this, we get a bunch of stuff. We also have the attention mask, which we're not going to use, but I put it in here because you can also use Blur to do your data preparation, and then you can create your own PyTorch loop or potentially use the trainer API if you want to do that too. So you can use the data pre-processing, data building aspects of Blur without using the modeling portions. So I keep this stuff in here just in case it's of interest to you. And so you can see that we have input IDs. And now we have something called aligned labels. And aligned labels is basically ensuring that for every single token, right, we have a label. And where that token is a special token, so it's a class token or a SEP token, we use -100. And -100 is basically tells cross-entropy loss that when calculating loss, ignore any labels that have -100. And of course, we don't want the special tokens to be included because we're not trying to predict the special tokens. So we essentially mask them for when the loss is calculated by setting the labels to negative 100. Also, once we add padding, we set the pad tokens to negative 100 as well for the same reason. And if you look at the tokenization in Blur, you'll see how that happens. So this is what we have for pre-processing. And as I mentioned last week, when we define our data block, we have two options in Blur here for token classification. And we're going to do this for all tasks by the time version 2 is released. Is we can go ahead and build our data block to use the pre-processed data, which we just created, which is our input IDs and modified labels, or we can use Blur as it has been traditionally built in version 1 to figure things out on the fly, which means that it's going to do the tokenization, create the input IDs and the appropriate labels at batch time. And so you have both approaches available to you depending on what you want to do. Here, we'll go ahead and take a look at what both of them look like. And fortunately, one of the nice things with the data block API is that they're going to look very similar. And one of the reasons I like the data block API is that, it's a blueprint for how to take your raw data and push it into something that's going to be modelable. Essentially, it's going to take raw data, and our end goal is to have data loaders that will allow us to send many batches of data at a time into our learner. And I like using the data block API generally versus the high level or the low level stack for creating your data loaders, because it just makes sense to me, like methodically the steps. And again, the nice thing with it as well is that it's going to look roughly the same, regardless of whether you do the batch time tokenization or the pre-processed, work against pre-processed data. So for batch time, we can go ahead and specify our token class batch tokenized transform. Again, this used to be called just before batch transform, which told you nothing about what it did. It is a before batch transform, but now we can see that what this does is handle tokenization. And we could go ahead and pass it into our text blocks, formerly named HF text block. Again, now it's just text block. We can say, here's our before batch transform, which is really going to handle the tokenization as needed, our input type for our show methods. And then in Blur, we also have a new token category block that's built off of the category block that fastai provides. But instead of trying to predict one label, it's going to assign multiple labels. And again, our labels are going to be the things that we defined above. And for every single word or every single token, once we get to this, it's going to have a label that's going to try to predict if it's not a special token. And then once we have our data block in place, we're going to eventually call data block data loaders and pass in our raw data set. But we can tell it here that it's going to get the X from the misnamed tokens column, and we're going to get our labels from the NER underscore tags column. We're just going to use random splitter just as an example here. I'm not setting seed, but that's also a best practice for reproducibility. And once we have our block, we simply call dblock data loaders and get our data loaders. And these are things I typically do in just my own work when I'm building anything deep learning, is I like to look at what a batch of data looks like. And you'd be surprised at how many times I find out it doesn't look how I imagined it would look. And this is kind of a good just sanity check to make sure that I'm at least putting stuff together in the right way. And so we can see here that we have a batch size of 4 with 156 tokens, because that's the max length of that particular batch. And then we also have a 4 by 156 tensor for shape, because we're essentially having a prediction per token. And then in fast AI, we can now do something nice like this: show batch, pass our data loaders, which is something you have to do with Blur, because I need information from the data loaders to show things correctly. And we can actually look at our words and see the labels that are assigned. And this is custom because for token classification, at least in my opinion, it's nice to look at each word and ensure that, yes, we're getting the right token assigned here, and have some confidence that not only is Blur working right, but also our data set's working right. So that's for just the normal on-the-fly batch time tokenization. We can also work with our pre-processed data set. So we actually created a pre-processed data frame above. And if we want to use that with just a few modifications, we can. And the biggest thing is we need to tell our batch tokenized transform that it's already been pre-tokenized, so it doesn't try to do the batch time tokenization. And if you notice in our pre-processing, one of the things we did was already include the special tokens. So we already have the class token and the SEP token, and whatever architecture you use, they're going to be included in the pre-processing. So we also need to tell the batch tokenized transform not to add any special tokens, which is super simple. We just add to our tokenizer quargs, add special tokens is false. Everything else is relatively the same, except we change our inputs. Our getX is going to look at the input IDs now, and our Y is going to look at our aligned labels. And if we run that through now with the procdf, and we can look at one batch, it's going to look pretty similar outputs in terms of the shape of the tensors. And we can do a show batch that works as before. And at this point, we're good to go to start modeling, and good to go for any questions that have popped up. So, Sonia, anything?
Yeah, we have a few. The first one is, there are a bunch. I'm trying to scroll up. Uh, do you imagine Blur being merged into fastai eventually? I shared in the chat that the official stance is we want to integrate. We being fastai wants to integrate better with Tim and Hugging Face.
Yep.
So
Good question. I don't know, and I'm not sure what the status of the next version of Fast AI is, but there's several things that Hugging Face does that Fast AI doesn't like out of the box, and the big one is working with dictionaries. And I know that Jeremy has mentioned that there'll be support in V3, and if there's support, I would love to see Blur integrated and made more part of the FastAI library, even if it's not the whole thing. But if the important bits were able to be incorporated, I would be all for that, because I wouldn't have to maintain this and break stuff and make everybody angry. It could just be Jeremy that makes everybody angry. And everybody likes Jeremy even when he changes everything on, whereas for me, it's not necessarily the case. So I don't know, but I have hopes that there'll be better support in V3 whenever that happens.
next question is by Mateo. Why setting the token values to -100 makes the cross entropy loss to ignore those values? What's the logic?
So real simply is that we only want to have our loss actually consider tokens that we want, that we actually we care about. And so we're not trying to predict the class token. Like, there's no label for that. There's no label for the SEP token. There's no label for the padding token. And so if we didn't set those to -100, then it would actually cloud and affect our loss. And I don't know how it would, but it definitely wouldn't help it improve. because we're including calculations on things that we really don't care about. And then when it comes to the actual labels, as I mentioned, when we break a word into multiple tokens, by default, we're using just the first token label for the loss and setting the other ones to -100, which basically is forcing the model to really put pressure on the first subtoken to make the prediction. And if you look at the course documents, this is used by a lot of folks just because it makes the loss a little bit more efficient to calculate because there's less things that you're having to include. And some researchers go with this approach. Others will go with the BI approach, which is naming the labels. Like if it's a person, like a first name, and it's labeled as B per, the tokens will be B per, and then I per for the rest of the ones. But you couldn't really do that when you do part of speech or chunking because they're not labeled like that. So I like the first token approach. That's something you can apply to POS, NER, or chunking. So I would say try it out, play with it, and see what your results are like. But yeah, that's
That
why.
made sense to me. Sorry, I was gonna say that made sense to me. So hopefully that would have definitely made sense to Mateo.
At least
Um,
it made sense to one person. That my day's accomplished.
uh, Money, who's an NLP expert, also part of the fastai community,
Yeah.
asks, "Do we always need to specify the return in the text block?"
Yeah. So it's not the return type; it's the input type that we're going to create. And the reason we have to do the input return type is that if we want to use I'll say this, it's not mandatory, but if you want to use any of the show methods, you'll need to use the right type there because you'll remember that the show type, like show batch and show results, are type dispatched. And so we're creating custom show batches that say, hey, if you see a token class text input, this is the show batch function we want you to run. So if you don't have to, but if you don't, your show methods won't work correctly.
That makes sense. There are no other questions. I just had one comment. I might be wrong about this, but I've seen a lot of CUDA errors. So the reason, as far as I understand, the error comes up for assertion when you don't mention the length is because CUDA likes, think of it like how TensorFlow used to be static graphs. So it likes to know the length and it really can't work with dynamic length. So probably that's why that comes up.
Yeah. The great analogy.
Yeah, I don't see any other questions. Please continue.
All right, awesome. Okay, so now we have our data loaders, and now we can start training. So the first thing that we want to consider is before we actually build a model and start training is how are we going to determine whether the model is really good or not, given our particular task and our objectives. And so one thing you learn if you go through the fast.ai course is that there's two things, right? There's two things that there's your metrics and there's your loss. And the loss is your model's way of understanding how good your model is, whereas the metrics are our ways as human beings for understanding how good our model is. And in general, what we care about are the metrics. And so we have to figure out like, well, what metrics do we use for token classification? And we have to consider this for every task, and they're different. And so one of the cool things I found out about last week is that on Hugging Face, there's actually a page of tasks that contains a lot of this information, including suggested metrics to use per task. And this is really cool. The link's going to be here in the slides, but if you just go to huggingface.co.task, you'll actually see like all the tasks we're going to be looking at in this study group and beyond. You're going to see the audio, some computer vision stuff. If we go to token classification, we get a nice example of what we're trying to do. We have a demo over here. We can actually look at models for token classification. data sets for token classification. And what I thought was really cool is this bottom part, which is what metrics to use for token classification. And I will tell you this, a lot of my work in building Blur and trying to support these tasks has been reading papers and on forums to try to figure out the answer to this question, which is what metrics should I use for really figuring out whether or not my particular task is performing well or not. So this is actually a really nice resource, if not just for this. And so, yeah, feel free to look at this as you spend next week looking at um, the token classification task, and maybe find some other data sets in here to play with. And another cool thing is you can actually like click on these and see the calculation for each of them, like how they're being calculated. So this is just really neat, and kudos to the Hugging Face team for putting this together. You've made all our lives easier just with this particular documentation. So yeah, token classification, keep that in mind. But yeah, so it mentions what are the key metrics, and it's going to be no surprise that when you look at Blur, those are the metrics that we support with a custom token classification metrics class in Blur. And it's built on top of the Seek eval library, which is also used in Hugging Face. If you use the datasets metrics, it actually, this particular task uses the same library under the covers, I believe. And there's different things you can choose from. And the answer as to which one to choose is it depends what you're trying to do. And so accuracy is a really common metric that we typically include, which is how many predictions did we get right. But if depending on whether we have a imbalanced data set, that may not be the best metric. We may want to dip down and use something like recall, which is measuring that when the label was X, how many times did we predict X? And again, a good example of when a recall is important would be an imbalanced data set, like predicting a rare is cancer class, right? If you just went with accuracy, you could predict 0 every single time and have a really accurate model that doesn't do the job you're expecting it to. So if we were trying to predict something like is cancer, or imagine in token classification, let's say we were like, there's an example I saw where they are actually labeling the names of drugs. And let's say that was really key because you were going to use the drugs identified for some downstream task. Well, recall would be a great metric to make sure you're getting those names, or having, or not the names, but having the is drug label assigned correctly. So if that's important to you, then look to recall. And a good way of thinking about it, recall is important when the cost of not acting on the prediction is high. So obviously, if you miss is cancer, you might have great accuracy, but you miss is cancer, that's going to be really bad for your patient. So the cost of not acting on the prediction is high. Precision is a little bit different. Basically, in this case, we're looking at when we predicted X, how many times was the label actually X? And we use precision when false negatives are less of a concern. And so an example that you'll see is like predicting is spam. We don't really care if we miss some of these, because if we predict something as spam, we're for email detection, we're not going to show that email, right? And so if we focus on a recall, we're going to be potentially identifying a lot of emails as spam that aren't, and our end users are going to be unhappy. We would rather those false negatives actually get to the user than a bunch of um, uh, false positives not. So in this case, we would look to precision, and we could think of this one kind of as the opposite of this. the cost of acting on the prediction is high. So if we act on, yes, this is spam, and we're going to have a lot more emails going into the spam folder, which we don't want. So again, this is going to be kind of task specific based on what you're trying to do. For the most part, I would imagine that for token classification, both are important, and so we would want to look more to the F1 score, which is a harmonic mean of precision and recall. So it's a score that kind of balances those two metrics and kind of, in a sense, gives us an average of the two. And support for all these metrics is baked into Blur. So just to show you what that looks like, and also to, again, kind of back my claim that Blur is fast AI, one of the things we have in the library is this token class metrics callback. And this is a callback deriving from the fast AI callback. And if you don't know what callbacks are, definitely look at the book, look at the course. Callbacks are probably the most important part of the fast AI library. And anything you want to do differently, anything you want to hook into, it's going to be a callback. And so you can see that in this particular one, I want to basically do the token, provide those token classification metrics that we just talked about. And one thing is this, the seek eval library doesn't predict or doesn't expect integers. It actually wants to look at the decoded labels. So it doesn't want to look at 7, 0, or 3. It wants to see beeper and what did you predict? Beeper, okay, good. So we have to do some modification here to get that, to actually use that library. Essentially, what we have to do is we have to decode our predictions. And that's what this callback does. And so you can actually pass, by default, it's going to do all of them, but you can pass what metrics you want to include and into this callback. There's some setup work that happens. It's using, actually, this is a PR I submitted a long time ago that allows us to create metrics in callbacks, not have to use the metrics API in Fast AI. And so what we're going to do is create a metric that's named after each of these particular individual metrics. So we're actually going to create 4 new metrics that we can actually use now in Fast AI, just like any other metric, but we're going to use the callback to calculate and assign the value. That's why it's called the value metric. And again, the callbacks just have hooks into all the life cycle of training. So, and you can override and access any of these hooks that you want, one or all of them. And here, the main one that we're looking on is after batch. And since we're really concerned about the validation set, I can check to see if we're in training, or in the case of inference, there's no labels and just return. There's no metrics that I want to calculate here. And from here, we can actually get the predictions. We can get the targets, right? And these are all tensors. And as I mentioned before, the seek eval library wants to work with the actual labeled names. And so we can actually go through here. We can ignore the ignore label tokens ID, which is again -100. And we can access our vocab, pass the prediction to get the related name from our labels list. And we can collect all these. And at the end of the validation batch is running, access this after validate hook. We can loop through these, and these are all the individual metrics that we want to calculate, right? Accuracy, recall, precision, F1. And we can pass them to this helper class called calculate token class metrics, We can pass the actual, these are not the identifiers, right? These are the labeled names, the actual labeled names for each token, the predicted label names from each token, and the metric key, which is going to be, for example, accuracy. And it's going to just call this simple function up here that is really going to send the work of calculating that particular score based on the key to the seek eval library. And you can see that this right here, just given this, what's nice is we can go back to our example. And we can define our learner. And again, just note some of the name changes. We have our base model wrapper that wraps our Hugging Face model. We have our base model callback that is part of our learners callbacks that is going to handle interpreting the output from the Hugging Face model, because this is actually going to return an object that has things in it, and optionally has already calculated the loss for us. So that's what this callback does. And then notice that for our fit callbacks, so these are callbacks that we're only going to use when we call, for example, fit one cycle. We're going to include that token class metrics callback that I just showed you. And the reason that we assign them to fit callbacks versus learning callbacks is that they're really not needed except when you're training. You can actually load these offline when you're doing inference later on, optionally. But when you export your learner, if we assign this as part of our learning callbacks, this gets included in our export, which makes our file a little bit bigger than necessary and not all that helpful. So we actually are just going to mostly assign metrics into our fit calls. So that's the metrics we're using, and I really encourage you all to look at the token class metrics callback to see how that works. It's a pretty good example of callbacks in general in fastai, which is what you're going to want to build to modify anything in the training lifecycle. So once we have our metrics all set up, we train our model. And the good news is that we train our models here just like we train any fastai model. And this kind of goes back to one of my fundamental design philosophies around Blur, which is to make it familiar to fastai developers. So this really is a library that's meant for folks who have read the FAST book and taken the course to be able to use and understand, like, oh yeah, I've seen these things before. I know exactly how they work. I see, oh, we can create a learner here. We can freeze it, right? So for discriminative learning, we're going to have different parameter groups and things that are probably early on and probably already have a good representation. Those are going to have weights that we don't want to change that much. Whereas our last parameter group typically refers to our classification task, which we're going to want to change a lot because it's going to be random initially and need the most adjustment. And so we can use those same concepts. We can use freeze, freeze to, or unfreeze. And we can also use the familiar ways of looking at our batches to make sure things look right. So I can go ahead and, after creating our learner, I could do a data loaders one batch. And now I can look at our predictions and make sure they make sense. And here they do. So we have a batch size of 4. We have a max size of 128, which we've hit. And we have 9 labels that we are actually predicting for. And so by running this, we can make sure that it makes sense. We can actually look at some of these things. Again, the first thing in our batch is our inputs, which is a dictionary. And this is one of the big reasons why Blur exists. And that is that fastai can't really understand dictionaries very well. And so we can see that, yeah, that's a dictionary. We can look at our input IDs, and there's a tensor of 4 by 128. And then we can go ahead and, as I mentioned, we can train our model. We can unfreeze it and train. We could train the frozen part. What's funny is that for different tasks, sometimes freezing I notice helps, sometimes it doesn't help that much, and it's easier just to unfreeze. For token classification, I've noticed that just unfreezing the model, which is how it comes actually, so it would just be not calling learn.freeze, actually works really well. And we can start training using fit one cycle. We can use this information and start training. Um, Notice that in general, I would choose the steepest part, right, which is maybe like 2 e neg 4. For some of the Hugging Face stuff, is I usually will go back about 10x. So I'll go back about, you know, I'd go back to about right here, which is about 3 in e neg 5, and start training here after unfreezing. So you'll have to experiment a little bit with the LR finder. Sometimes exactly what you think is like for a standard fast AI model, which would be somewhere where it's really steep, right? Or to go here and go back 10x, right? Is one of the recommendations. You'll find that going back a little bit further, like another 10x, is often a good place to start with the uh, transformer models, especially if you're just going to unfreeze the model. So just be aware of that. And you can see that our metrics that we defined, we're getting them here as we go through each epoch. We're getting our accuracy, precision, recall, and F1. And this is calculating the overall accuracy, precision, recall, F1 across all labels. But another thing we can do here with Blur is, and this is part of the learner in Blur, is look at the token classification report, which allows us now to look at those metrics per token, as well as looking at the micro, macro, and the weighted average. And the support tells us how many times that token appeared in the examples that we looked at. So we can verify that we can see whether or not we have a imbalanced issue. And you can see here for the MISC label, there is a slight imbalance. So this is something that if this was really important to us, we might want to do something to handle that imbalanced data, or maybe even spend more time looking at the recall metric over the other ones. So we can look at the per token metrics, and then we can actually also look at call show results, and we can see how did our model do. And again, we're only working on a subset, so it's not going to be that great, but it actually turns out to be pretty great already. And so we can actually see that, yeah, we're getting these things correctly. So we have Monica Sellis, and there it identified Monica appropriately with the B per target, and we have this is the token, the target label that we're trying to predict, and what our model predicted. And so we can see it actually did a pretty good job here, at least with these two examples. Any questions come up on model training?
No, I don't see any questions.
Oh, good. All right. I figured, because that's the most like similar. Like there's really nothing different there, and it's mostly kind of like learning through experience and playing with that to see, hey, what we have different options for fit, right? We have different optimizers. Like some people like using Ranger. I still think Atom works great. You could do fit. You could use different learning rate cycles. So you can use fit one cycle, but there's other ones supported. And once you're at this point, you really can experiment and play with those, just like you're used to as a FastAI developer. So
Boris did a thread around what optimizers people are using. Did you get a chance to see that?
what's the optimizer called?
No, he was just asking what optimizers
Oh,
people are
yeah.
using.
Yeah, I think I saw that post, and I think like I saw folks with mention Ranger, And still, like for myself, I get great results just using the optimizer that fastai gives us. But another good, that now that you mentioned that, another good place to kind of figure out good defaults or ranges of values to try for any hyperparameter is looking at the papers. And if you're scared that you're not going to understand it, don't be. I don't understand a lot of the papers. When it gets into the math and the latex and the Greek, I am like, oh my God. And I'll Google some things. But fortunately, most authors, even in complex papers, do a really good job describing their approach. And almost always at the end of the paper somewhere, they have like the hyperparameters that they got the best results with. And
Yeah.
so that's always a great place to look if you're trying to figure out, what do I choose for learning rate or weight decay, or for epsilon? What do I actually look at? So
I found the thread. If you could let me see how do I send you the link? Can you open this
oh yeah,
link? That has the discussion.
I got it. Did you want me to show folks?
Yep.
Go ahead and go here. Oh yeah, nice. Yeah, I'll stick this in the slides as well, so folks can go through. This is another good resource right here. If you're not sure what to do, like the ML Twitter community is really awesome, and if you post a question, and even like it's actually good to like mention the Hugging Face folks, you'll usually get somebody that replies with some helpful information and resources. So this is my approach a lot of times. Like when I first started with Hugging Face and was just doing sequence classification, I was like, how do you figure out hyperparameters? Because it's a little bit different than the stuff you like with using an LSTM. It's different than computer vision or tabular stuff that you get exposed to in fastai. And got a lot of good feedback, from people that had done the hard work before me, and kind of like discovered like, oh, sometimes you think the learning rate's this, but really go back about 10x. Or don't worry about freezing and training and then unfreezing, which is the typical fastai approach. It's just
Yeah.
better to unfreeze and you'll get better results. So yeah, Twitter is an awesome place to do that. So yeah, great link, Sanyam. So yeah, I'll put that in the slides as well.
Thank you. I've shared the link to the report that came out of this. By report, I mean a blog post, and they compared different optimizers. So Boris was working on Dolly Mini, and apparently Shampoo, which is the name of an optimizer, was really good for that.
Oh wow. Oh cool. I haven't heard of that one. Yeah. So yeah, there's a lot out there and a lot of people doing really interesting research. Boris is one of the people to follow. Always doing like really interesting stuff, especially with this Dolly. I've been watching that. I always like how it trains. It takes a while to train, and so he would give updates, on how it was looking. So
Yeah.
yeah, he's a great resource.
So, sorry to go off on a tangent.
No, those are good tangents. So all right. So once we've trained our model, well, the last step is inference. And again, we can use the same approaches to inference that you've already seen in fastai, which means we can export our model and call predict. With Blur, we actually include a helper function that we associate to the learner class called Blur predict tokens. And what this does is allow us to do inference and give you the same results as if you were using the token classification pipeline from Hugging Face. And this is a little bit different than version 1. And I like it better. And also it creates a nice parallel with Hugging Face. So that if you're using the pipeline and you're using Blur, the results are going to be the same and can therefore be used in the same way. So we'll look at how that works in just a moment. But also I want to mention there's other options. You could actually deploy your trained model, because at the end of the day, the model that you're training is just any regular old transformer model. You can push that to the hub and then be able to use that in the pipeline function yourself. So that's an option. if you're doing inference on batches of data at once, which is typically what I do. So I get a Excel file or a CSV file of thousands, tens of thousands of text items that I want to do inference on. Probably the best approach is to either just create your own PyTorch loop and iterate through there and get your predictions just using pretty much standard PyTorch. Or you can go ahead and use, I'm sorry, it's not leader, it's learner.getpreds. Oops, let me fix that before I forget. And create a test data loader. And the test data loader allows you to really simply allows you to create a data loader modeled after your validation data loader. So there's no augmentation applied, there's no sorting, and you can pass an additional set. So you can pass another, if you're training, like let's say on data frames, and you get a CSV file of a bunch of data you want to do predictions on, you can convert that to a data frame and actually pass that to the testDL function, get a data loader, and run it through learner.getpreds, process the predictions however you will. That's another kind of approach to doing the batch time inference. So maybe if there's folks that are interested, as we get to the last session, I can show you an example of what both of those approaches would look like for a given task. But what we will look at is, if you hear crying in the background, that's my dog, and I apologize. If we look at just the real-time inference, we'll pull up an example, and just to show how this works here is, I got the first text. Sanyam is a great host who also works at Weights and Biases. And text 2, fastai is an awesome library built by Jeremy Howard from Australia. And we can pass those to blur predict tokens. So you can actually pass one or multiple texts that you want to get predictions. And then we can iterate through the results. And you can see these look just like the pipeline results. So here you can see it didn't do a perfect job with your name, Sanyam. So we probably need to train this more. It broke the S and the Anyam part, but it did get weights and biases correct. And what's interesting, when I see things like this, I go like, why did it break that apart? That's interesting. And there could be multiple reasons, and they include potentially that the name Sanyam is very unique. And this is, again, everything's, this is an English grammar, so I doubt it has seen Sanyam in there. And it also may be that we're just using a subset, and we need to maybe use the full library and spend some more time kind of training it, and also maybe need to give it some Sanyam examples in there. So, yeah, when you look at these things, it's, make sure you really think about all these things, because these are all factors, right? And so, yeah, so those are my thoughts. There might be other reasons, maybe a better architecture that we could choose. Maybe a multilingual architecture would do a better job, right?
I don't agree with the statement, but it got weights and biases right. So at least that's what matters. So
that's all that matters. You got that one right there.
Yeah.
And you got most of your name. But you can see, like, Jeremy Howard, right? That's a kind of more English sounding name, and it got that one correct. And it didn't identify fastai as an organization, which is interesting. And I think if we actually trained this against the full data set and gave it more examples, it probably would get this right. But it did get his name and the location right, that Australia is a location. It did get that one right. So anyway, so blur predict tokens gives you the same thing as the pipeline. And as I mentioned before, if you want to deploy this and build your own API and actually do token classification, it's going to work just like any other fast AI trained model, we can go ahead and define a export name. We can call learner.export. It's going to create a pickle file with everything needed to reinstantiate that learner. And we could call load learner, pass that pickle file, and to create an inference learner. And once we have this, it works just like our any other learner. We can call blur predict tokens and get results here. So we can actually now deploy this into an API, create a web application, call this in our API, and get predictions. And that is the final step in our end-to-end training of a token classification model. Coming soon to Blur. So again, I'm going to update the previous examples with the new namings of a bunch of things so that you don't have to wrestle with that too much. But with regards to token classification, we're going to add chunking examples and experiment with how well that works and helps with handling long documents, and also finish up support on the pre-processing front for both data sets and data frames. Right now, the data frames pre-processing is good to go. And data sets is something I haven't really spent much time with, but that's going to be coming soon as well. So just be aware if things don't work right, look at the at GitHub and see if there's actually support. If you want to contribute, that's even better. It's less work for me to do, and I would appreciate it. So just keep that in mind that those things are coming eventually. For homework, we covered an ended example of token classification. You could use the bits right now in Blur and create a train a token classification model that you can deploy in an end user app. It's however you want. It could be web app. It can be something that you can use like in Gradio, I think, like that Hugging Face, like Spaces. I haven't really played with it too much, so I don't know how that all works. But we've looked at the end-to-end example of token class models with fast.ai. But I encourage you to go through the official course and kind of look at the segments that talk about token classification and offer more details about how it works, how you can use some of the other methods to train models and deploy them to the hub. And I have references to each of those 3 sections. Also, this week, go through the course and try training your own token classification model. And even better, prove that you really understand it, at least to yourself, by helping others in the writing of a blog to explain how you did it and what you found difficult or easy, or are things that you found that you wish that you were told ahead of time before you had to find out on your own. And you might want to try using one of the data sets from that task page in Hugging Face and do something a little bit different than use the data set that we went through today. And lastly, because metrics are so important in terms of really evaluating your model, we looked at the core token classification metrics. Go back through those, make sure that you understand them, and really prove that you understand them by explaining it to someone without a machine learning background. So if you can do that, then you really got it. So I'm putting that as some homework as well. And that's it. I have nothing else unless there's some questions that have come up.
There's just one question. When to use custom NER classification versus something from Spacey?
I don't have a good answer for that. I'm not sure. And I'm sure custom NR, you mean custom NER, so named entity recognition. I really can't answer that specifically, except to say that if you're a Spacey user and it works well enough, go with that. If you think there's potentially, let's say it doesn't work well, or you think there some serious improvements can be made, like you have some like a lot of customization, maybe go through building your own. So I think it depends.
Okay, thanks for that answer. Also, some people have mentioned they're not getting the email with the resources. I'll request the team to double check. Maybe I said something stupid in the automated emails platform, whatever it's called. So that might be on me. I'll make sure you get them this time.
Are you talking about like the links to things or? Oh, okay, yeah. I had some people
We
ask that too. Yeah, on the forums.
It's supposed to reach via email. Maybe I did something stupid. That's why it's not going through. So I'll ask
Yeah,
the team to
yeah,
look into it.
yeah. I also post the links on the Discord. So if folks don't get it or lost their email, I try to put them there too. Especially if people remind me. So I've had a few reminders and try to get those up there as well.
Awesome. Which callback scenario should we use for fit underscore CBS?
So the ones that are typically, so it really depends. I mean, most callbacks can be put in either as learner callbacks or fit callbacks. Anything that is not needed for inference, I tend to put as a fit callback because it just makes that export file bigger. And sometimes there are things that are you can't pickle that are part of those fit callbacks. Like I do have some metric callbacks I use. I think is for summarization, um, where if I put them as a learner callback and then call learner.export, it just bombs. And the reason it's just not a pickleable class. And so by putting those in fit, you're just using for fit. So they don't have to be capable of serializing to pickle. And so metrics are good candidates. Any callbacks dealing with metrics are good candidates for a fit callback.
Awesome. Thanks for that answer. I think this would be the last question. Can we use Blur for NER tasks in production?
Yes, but be cautious. I don't think the token classification bits that I showed you today, and again, this is in the alpha version 2 build, right? And I don't think the token classification bits are going to change much from what you saw today to what it will be in the final version. So I will say maybe. But if something breaks in a couple weeks, you only have Sanyam to yell at, not me. So yeah, I think I'd be cautious, but I want to say that yeah, you could, but just keep an eye on it.
That's a fair deal. Um, let me make
That's a
sure.
good political answer right there. Maybe yes.
Awesome. With that, I'd love to wrap up, and I just want to thank the audience and also Wade. I like celebrating small accomplishments, and I like setting myself up to stupid goals. So my goal was to do 10 lectures in 9 days. I've done more on the podcast, but podcast is easier for me. This is a bit harder, and I'm so grateful I get to collaborate with people like Wade. I'm so grateful everyone comes to these events, and I couldn't have done it at any place. I could have done it elsewhere as well, but I wouldn't want to do it at any place other than Weights and Biases. So I just want to thank the community for coming to our lectures. Really thank Wade for hosting these series, and it's such an honor to contribute to the community in this capacity.
Yeah, this is awesome. I appreciate the opportunity as well. And even though I can't see anybody's comments or see anybody, thank you for attending and being a part of it. I always go back to the YouTube to see if there's things that I miss. So I will look at things, but I can only multitask so much. But yeah, thanks, Sanyan. This has been a lot of fun as usual.
Thanks to you, and thanks everyone for tuning in. We'll see you next week.